So just a couple more sections on chapter 3. This is Newton's method. You have probably heard of Sir Isaac Newton, and this is his method. This method is all about finding zeros for, a function that may be hard to find. You can't factor it, or, if it was a trig function or something and could pretty simply find out, its roots, how could you do it? And so we're going to consider an equation like this, x to the fourth plus x minus 3 equals 0. You can see that that's not going to factor. You can't just look at that and say, oh yeah, I know what values make it true. So Newton came up with this method. It's based on calculus and the idea of derivatives, and it can help you find the root of any equation, or roots if there's more than one. So the first thing it says is set the equation equal to 0 if it isn't already. This one already is, but it really just means bring everything to one side. And then consider the function that is, in this case, the left-hand side of the equation. So we consider this polynomial x to the fourth plus x minus 3. And we look for the roots. So our goal is to find what are the roots of the function, the same as saying when is the function equal to 0. That's our goal. So in order to do this, what we do is we take a guess on the root. So we guess what's called x1. And we say, I think that this is where the graph crosses the, the x-axis. So we check and we say, does in fact the y value equal 0? If it does, you're done. But of course, it's not typically that easy. So if not, what we do is, here's the calculus part, we draw a tangent line to the function at that value x sub 1. So notice that is on our graph here, that is this line right here. So this is the point, and you can see the tangent line that's created by doing the tangent line at x sub 1. Notice that as that line comes down, it now intercepts the graph, that line, at what we're going to call x sub 2. So intercept is at x sub 2. And the key thing to see is that x sub 2 is closer than to the actual root than x sub 1. And then the idea would be you could keep going. So look at the tangent line at x sub 2 and how it then crosses the x-axis at a value called x sub 3, and that's even closer to the root. And so basically we do this iteration of the idea of the tangent line until we get to a point where a lot of the values that we're coming out with are agreeing to a lot of decimal places. And of course, every time we just check and say, does this value give us 0? Because if it does, of course, we know that we actually have the root. Now, typically these roots aren't pretty, because if they were pretty, we'd be able to factor or something and find them. So then the question is, what is this x sub 2? Like, how do you find that, and what is it? So what we're going to think about is the idea of the tangent line. Again, this is where the calculus comes in. So make sure you have this, and I'll be, of course, using the space below. Okay, so the first thing we think about is just the equation of a line that goes through our function at the point x sub 1. So remember, equation of a line, y minus y1 equals mx minus x1. Now, in our case, we're talking about x sub 1, and then the y value for that we'll just call f of x sub 1. And then the slope at x sub 1 will just be f prime of x sub 1, and then x minus x sub 1. Okay, so this is the equation of this line. Now, what you want to understand is that tangent line at x sub 1 has an intercept at x sub 2, and the point is x sub 2 comma 0 because it's a root. So we're going to replace our x and y with the idea of x sub 2, 0, because we specifically want the point where it goes through the tangent line and then through that root point. So we'll have 0, f of x sub 1, f prime of x sub 1, and then x sub 2 minus, x sub 2 minus x sub 1. Okay, and then the idea here is really just we want to solve this for x sub 2 because we want to know what is the actual root that we think we have now found. So in order to do that, I'll manipulate things a little bit here. So I'll have f of x negative minus f of x sub 1, and then I'll have f prime of x sub 1 times x sub 2, and then a minus f prime of x sub 1 times x sub 1. And again, I'm trying to solve for x sub 2 here. So notice what we're trying to solve for, because it's basically like we're just finding, this whole Newton's method is just finding numbers. So we just need to solve for x sub 2. So I'll just bring things to one side, bring things to another side until I have x sub 2 by itself on one side. So I'm going to bring this over, negative f of x, f prime of x sub 1 times x sub 2. I'll bring over the other piece, f of x sub 1, and then minus f prime of x sub 1 times x sub 1. And then dividing the whole thing by a negative f prime x sub 1 is going to give me x sub 2 f x sub 1 over f prime x sub 1. And then there's a negative on that, so I'll put that here. And then dividing out the next piece is, hopefully you can see that, is just going to give me x sub 1, because the f prime of x sub 1's simplify to 1, and the negative become positive. So we end up with this. So let me write that like this. This is typically how you'd see it. X sub 2 equals x sub 1 minus f of x sub 1 over f prime of x sub 1. So the point is, your new root is simply your old root minus the y value at the old root, the x sub 1, and then divided by the derivative at x sub 1. And that would be your x sub 2. And then you could continue to do this. So as an example, you could probably not too surprised to find that x sub 3 is equal to x sub 2 minus f of x sub 2 over f prime x sub 2. So you have to do each iteration separately. Eventually you're going to get these values of x sub 4, x sub 5, x sub 6 closer and closer and closer to the actual root of the function. So what Newton's method says generally is, as you can see, when you're looking for your next root, x sub n plus 1, you're just using the root prior, x sub n, minus f of x sub n divided by f prime of x sub n. Not sure why I wrote 2 there. Let me take it off. Okay. So now all we have to do is use it. I mean, this is, again, a way to find any roots if you did not have them in an obvious way. All right, so let's take a look at an example with what we have, the example we have at the top of the page. So solve that using Newton's method with x sub 1 equals 1. Now it says in general we go until 8 places agree. That decimal places agree. That is a lot. I understand that. Typically I'm just going to ask that students can use the iteration a few times. Can you, show that you can keep going, a couple times and see what you get. So don't worry too much about having to do this like 10 times or something. You would not have to do that. But here's our idea. So we are going to consider f of x equaling x to the 4th plus x minus 3. And we are being given the x sub 1 equals 1. And in general, it's not uncommon to be given an x sub 1. Really, you should be able to start with anything as long as it's not too far away from the actual root. So you can see, like, if we put in 1, you can see that we're going to get a negative 1. So of course that's not 0, but it's not like super far from 0. So it's not surprising that this will start working, pretty quickly. So we have f of x. We also need f prime of x. So you can take your derivative. Remember to pause anytime. Okay, so what we do is the first iteration here is simply going to be what we need is we need f sub 1, and as we already said, that's going to be a -1. We need f prime of 1, which we can see is going to be 5, so just putting that into our derivative. And then we are able to use Newton's method, which says that x sub 2, the next closest value that we believe is the root, is simply our x sub 1 minus, and then f of 1 divided by f prime of 1. So you can see that it's going to be 1 plus 1/5. 1/5 is 0.2, so we get 1.2 as what we believe is the root for x sub 2. Now, if we plug that in, remember we got -1 when we plugged in 1 to our original function. But if we plug in 1.2, again, back to the original, we're going to get 0.2736. So see, we're a lot closer to 0. That y value of 0 that we're looking for, we're a lot closer. Now, we can do this again. So the second iteration is simply going to be, now we have to use, instead of 1, we're using 1.2. So we need to find f of 1.2, f prime of 1.2, and we see what we get when we do that. And then those are the values that we use, including including x sub 2 that we got. Now remember, you already have, if you've checked your value, you already have this value right here because it is just the y value. And then you put this into the derivative, and in this case I get 7.912. And then I'm ready to do x sub 3. So I simply take my x sub 2, which is 1.2, I subtract 0.2736, and I divide by 7.912. And in this case, you'll start seeing that you're going to be getting like numbers that are just, you know, decimals, and that's not surprising. So let's put it in. Make sure you get the same thing. 7.912. Okay. And it looks like in this case we get 1.165419616. So definitely, you know, a lot of decimal places there. If we check that value, just due to space, let me just I'm going to check that value. And when I do that, I get 0.010134681. So I'm putting that back into my original to say, is this the root? How close is it? So again, notice I'm getting even closer to getting 0, but I don't have 0 yet. And I'll just tell you what the other iterations are, because once you kind of get the hang of it, it is what it is. But for x to the 4th, if we did all that work, we would get 1.16403726916. So if you want, you can check and use the Newton's method and see if you can get that. So notice that, remember x, kind of thinking about what we're doing here, we're finding that root. So we have our x sub 2, here's our x sub 3, here is x sub 4. So notice we're starting to agree to more decimal places just by doing a few iterations here. And then if we were to do x sub 5, again, I'm just kind of letting you know what these values are. 16403514029. If you did another iteration, so you can see it starts getting, you know, a bit much. X to the 6th, we have 1.1640351. So notice the amount of decimal places that are agreeing here. Once you get to that x to the 6th, you actually agree. That should be a 9, that should be a 9, not a 6. So we're actually at the point where we're agreeing here. So it takes a few iterations, and again, the closer you are originally, the easier it's going to be. But we can see that the root here is, in fact, something like this, you know, like this is correct to this many decimal places. And if we were to say for example test x sub 4, so I put that in 1.16403726916. This is 1, 2, 3, 4 zeros, 1, 5, 5, 6 when you put that back into the original. So we're getting very, very close to the idea of this is the actual root, and that's what Newton's method does, and that's what it helps us with. So it's a way for us to find all those roots of a function that may not be rational, basically. Okay, so here we have another example. Notice that this section is only a couple pages because there's not really anything too exciting with it. It's just, it is what it is, and once you learn it, you got it. So just kind of know how to do it and then move forward in your life. But in this case, notice we do not have everything to one side. So the first thing we would want to do in this problem would be to bring everything to one side. X cubed minus 1 equals 0. And then we'd want to consider that function, f of x equals 3 sine x minus x cubed minus 1. And then we're also being told to guess x sub 1 equals 0. So that's just to help us out and be more consistent, because then we all have like everything we need. We're also going to need the derivative, f prime of x. And this is going to be derivative of sine is cosine, so 3 cosine x minus 3x squared. So we're going to be plugging in values to our f of x and our f prime of x. Other than that, everything's the same. So we have our x sub 1, our x sub 2, and this is another way to kind of write it, but it would be 0 minus, and then f of 0 divided by f prime of 0. That's what it looks like. So 1 minus, and then f of 0, if we put that back into the original, it looks like we're going to have a negative 1. And if we put 0 into our derivative, cosine of 0 is 1, and then the 3x squared will be gone, so we get 3. So we get x sub 2 equals 1/3, and that would be our first iteration. And if we plug in f of 1/3 back into our original, if we find f of 1/3, we can see that we're going to get negative 0.05545. Now when we put 0, of course, into our original function, we get negative 1. So again, you know, we're trying to get closer and closer to the idea of 0. If we do x sub 3, we are going to be taking our x sub 2 and then just subtracting f of 1/3 divided by f prime of 1/3. So it's always just the same. So you can put that into your calculator and see what you get when you do that. But make sure you're in radians. We are doing, you know, radians in this. You're not seeing any kind of degrees. So we'll have 3 sine of 1/3. And then minus a 1/3 squared. So 1/3 cubed, excuse me. 1/3 cubed minus 1. All right. I don't know why I did that, because so we already know what f of 1/3 is. It's negative 0.05545. And then if we put 1/3 into our derivative, 1/3, and then minus 3 times a 1/3 squared, and we see what we get there. So again, these numbers are going to start becoming kind of bigger. So we have 50, so 2.50, 1537506. Ooh, yeah, okay. And then we do that. I put a lot of decimal places because that's going to be, you know, a more exact answer for these iterations. I get 0.35550. So notice 1/3 is 0.3333333. So I'm not that much different from that. So I'm getting closer to whatever that true root is. But if I put that 550 into my original function, I'm going to get a negative 0.000750744. Okay, so I'm getting closer and closer to 0 here. That's the idea. Again, I'll just kind of let you know if you want to practice it and you want to see. If we do this iteration again, we are going to get x to the 4th is going to be 0.3558, 0.8532, looks like I have a 4. If we were to do x to the 5th, so another iteration after x to the 4th, we're going to have 0.3558085942. So notice just a little bit different than what we had from above. So it still agrees all the way to there, which is quite a few decimal places. It's 7 decimal places. So we can tell that we're really close. And if we were to look at the actual root, so if we were to find the actual root of this, so the actual root is r equals 0.3558085942. So it is actually the x to the 5th. So it took 5 iterations to get there. So, make sure you know how to do the Newton's method, understand what it is, understand what it's trying to do and how it's trying to help you. And there's only one more thing we want to talk about with this, and then we're done. So there's a theorem. Newton's method always converges to a root r of f, provided that f prime has no vertical asymptotes at r, and provided x is chosen close enough to r. So those are the two things that you'd want to happen. And we're just going to look at a method, an idea here. If we think about f of x equaling x to the 1/3, and we're going to guess x prime, or x sub 1 equals 1, we need f prime of x. That's going to give us 1/3 x to the -2/3. So what I want you to see pretty quickly here is that this is the cube root of x, so you probably know, I'm going to try to do it backwards here, that this function does this. And although it's continuous everywhere, there is an issue at 0. And you can think about what that issue is, or you can graph this and think about what that issue is. But it does go through 0. You can see that 0 for x gives you 0 for y. So we know what the actual root is. It is x being 0. However, watch what happens when we use Newton's method on this. So x sub 2 is going to be x sub 1 minus, and then we have f of 1 divided by f prime of 1. And that's going to give us f of 1 gives us 1. F prime of 1 is going to give us 1/3. So we actually get 1 minus 3. So 1 divided by 1/3 is 3. So 1 minus 3 is a -2. All right, so, okay. And then if we try to do x sub 3, we get -2 minus f of -2 over f prime of -2. So -2, f of -2 is going to be, -2 to the 1/3. And that's going to be divided by, yowza, 1/3 times -2 to the 2/3. All right, so believe it or not, if you were to simplify this, you actually get 4, because -2 to the 2/3, the idea there is you could flip them because you are dividing by a fraction there, so you could flip it, and that's actually going to give you -2 to the power of 1, which is -2 times 3 is -6, and then -6 is 6, so -2 plus 6 is 4. So you get 4. It might not be enough for you to guess the next values, but if you were to guess, you might guess the next value is -8, and if you did this another time, you would get, as you can maybe guess at this point, you would get 16. So the point is we are bouncing. You should see that the Newton's method here is not taking us anywhere. It is bouncing. And if you see the pattern, in fact, the next iteration of Newton's method is going to give you, it's going to be a -1 to the something, and then 2n minus 1. So there is a pattern to these, but none of them are actually getting you to a value. And the reason is, so Newton's method fails because f prime of x has a vertical asymptote at r equals 0, so the root of 0. And again, you can think about what that looks like. There's this vertical asymptote at that value, and it's a vertical tangent, you know. And so because of that, Newton's method fails. It doesn't follow the theorem, so you can't use it. So in general, you can, and it's a really good method. Obviously, it was the only thing that people could use before there were graphing calculators and other things like that. Now that we have graphing calculators and computer programs, they can do these things for us, but this is where it comes from, and this is what the calculators and the graphing programs would actually do to get these roots for us. Okay, I didn't say anything really weird or exciting for the quiz, so I'll just mention that yesterday I bought these beautiful flowers at Trader Joe's. The line was not too long to get into the store. Everything was very safe, and so that will be on the quiz, so just remember that. And that is the end of section 3.8.